For decades, defeating an incoming aerial threat relied on a predictable, linear calculation. To survive an air attack, a defending military had to intercept the target with a weapon that was significantly faster, more accurate, and more advanced than the target itself. These sophisticated interceptors, like the PAC-3 fired from a Patriot battery, are marvels of modern engineering. They take years to manufacture, require highly specialized supply chains, and cost anywhere from $500,000 to upwards of $4 million per missile. The Iranian Shahed family of unmanned aerial vehicles is engineered entirely to subvert that specific calculation. The most recognized of these systems is the Shahed-136. It is a one-way attack drone, often called a loitering munition. Instead of prioritizing survivability or advanced evasion, its design maximizes mass production and extreme cost-effectiveness. This ledger illustrates the fiscal discrepancy. One Shahed-136 costs $50,000, while an interceptor costs $500,000. The drone is destroyed, but the defender absorbs a massive loss. Against a massive swarm, the defender's financial reserves and interceptor stockpiles are completely exhausted. The attacker forces the defending nation into an impossible position. Even if the defender intercepts 100% of the incoming swarm, the attacker still achieves an economic victory by bankrupting the defense. They win the engagement without a single drone ever reaching its physical target. This economic asymmetry is a strategic tool. It allows a nation operating under severe international sanctions, with a comparatively small defense budget, to project significant power across a region dominated by wealthier, technologically superior militaries. The Shahed is not built to outmaneuver a fighter jet. It is a mathematical exploit intentionally engineered to exhaust the ammunition and budgets of modern integrated air defense systems. To deploy these drones in the necessary volume, Iranian engineers had to aggressively cut manufacturing costs. They did this by relying heavily on COTS, or commercial off-the-shelf components, parts designed for civilian use rather than strict military specifications. This 3D wireframe shows the construction of the Shahed-136's delta wing airframe. Notice the complete absence of aircraft-grade aluminum. Instead, the body relies on a cheap internal honeycomb core, molded with mass-produced carbon fiber cloth. Using fiberglass and carbon composite slashes the unit cost, but it provides an inherent tactical benefit. These non-metallic materials naturally reduce the drone's radar cross-section, or RCS. RCS is a measure of how detectable an object is by radar. The smaller the cross-section, the less radar energy the object reflects back to the receiver. Panning to the rear of the airframe, we find the primary propulsion system, the Motto MD-550 engine, driving a simple two-bladed wooden pusher propeller. This 50-horsepower, four-piston engine is not a specialized military design. It is a reverse-engineered clone of the German Limbach L550E, a power plant originally built to fly civilian light aircraft. This reliance on cloned civilian engines extends to the Shahed-131, the slightly smaller precursor to the 136. Rather than a piston setup, the 131 uses the Surratt-1, a 38-horsepower rotary Wankel engine, copied directly from existing British and Chinese commercial designs. Both power plants share the same severe vulnerabilities. They limit the drones to a sluggish cruising speed of roughly 185 kilometers per hour. Furthermore, because they are unmuffled two-stroke combustion engines, they generate an incredibly loud acoustic signature, often alerting targets minutes before the drone is visible. Once airborne, the drones fly entirely blind. They carry no electro-optical cameras, no thermal imaging, and no active radar seekers for terminal guidance. Navigation is handled by standard commercial GNSS modules, global navigation satellite systems, like civilian GPS. To counter electronic jamming, the drones carry a backup INS, or inertial navigation system. An INS uses internal motion sensors and gyroscopes to calculate position by dead reckoning if the satellite signal is severed. Every feature of the drone, the moped-style engine, the fiberglass shell, the lack of a camera, represents an engineering compromise strictly optimized to protect the system's most important capability, its incredibly low price tag. Because they are built to be expendable, Deploying them into combat requires none of the infrastructure associated with a traditional air force. There is no need for paved runways or hardened military air bases. Launch operations are highly decentralized. Crews mount simple, static firing rails inside standard commercial shipping containers or on the back of civilian flatbed trucks, allowing them to fire from remote highways and drive away before they can be targeted. To get off the rail, the drone uses a solid-fuel JATO booster. JATO stands for Jet-Assisted Takeoff. A small rocket attached to the belly fires for a few seconds to provide initial flight velocity, burns out, and is immediately jettisoned so the propeller engine can take over. This tactical map visualizes the doctrine of channel saturation. Modern fire control radars are highly advanced, but they obey physical limits. A battery possesses a finite number of radar channels it can process, and a fixed number of missile tubes ready to fire at any given second. By launching 50 or 100 Shaheeds simultaneously at a single geographic target, like a power substation or a runway, the attacker intentionally feeds the defense more targets than the system's hardware can process. These swarms do not fly in straight lines. Operators program them using multi-vector geometry. The drones take circuitous routes, designed to converge on the target simultaneously from entirely different azimuths and altitudes, creating a chaotic 360-degree problem for the defense. To survive the journey to the target area, operators employ NOE, or Nap of the Earth evasion tactics. By hugging the terrain, tracing riverbeds, and flying at extremely low altitudes, the drones exploit the radar horizon. The curvature of the Earth and the physical terrain block terrestrial radar waves, shrinking the defender's warning window from several minutes to mere seconds. The math of the swarm is absolute. By overflowing the tracking bandwidth and depleting the ready ammunition tubes, the attack guarantees that a percentage of the high explosive payloads will break through the defensive net. In complex joint operations, those slow, loud kamikaze drones actually serve a different purpose. They are not the primary strike weapon. Instead, the 136 acts as a sacrificial vanguard. It is sent first specifically to draw fire, force the defenders to engage, and map the layout of the enemy's air defense network. The moment a defending battery activates its radar to track the incoming swarm, it emits powerful electromagnetic waves. By turning their radar on, the defenders instantly broadcast their exact geographic coordinates to observing intelligence assets. Once the defenders are distracted, reloading, or out of ammunition, the attacker exploits the gap. They launch a secondary wave, featuring the highly advanced Shahed-138. The 238 trades the sputtering piston engine for a micro-turbojet. It cruises over 500 kilometers per hour and can reach velocities up to 800 kilometers per hour during its terminal dive, drastically reducing the time anti-aircraft gunners have to react. This propulsion upgrade eliminates the economic asymmetry. At an estimated $1.4 million per unit, the 238 is no longer a cheap tool of attrition. It is a high-value precision asset. To protect that investment, the 238 can be equipped with a specialized anti-radiation seeker. This sensor is explicitly engineered to lock onto the specific electromagnetic frequencies of the radar emitters that the defenders exposed during the first wave. The cheap, loud 136 acts as a battering ram, forcing the enemy to raise their shield and reveal their position. The jet-powered 238 then follows the radar beam back to the source, destroying the battery and permanently blinding the sector. The sheer volume of Shahed-136 deployments commands global attention, but focusing only on the kamikaze tactics obscures Iran's broader military capability. They have heavily invested in advanced multi-role unmanned platforms. This is the Shahed-129. It represents Iran's operational entry into the MALE category, medium-altitude, long-endurance combat vehicles. Unlike the blind, coordinate-driven drones, the 129 carries a chin-mounted sensor array to feed real-time video back to ground controllers. Powered by a 4-cylinder aircraft engine, it can orbit a battlefield for 24 continuous hours and engage targets of opportunity using its 400-kilogram payload of precision glybons. The absolute apex of the current engineering family scales this concept up significantly. It is the Shahed-149, widely known as the Gaza drone. The 149 steps into the HALE category, high altitude, long endurance. It is a massive platform, utilizing a 750 horsepower turboprop engine, rivaling the physical size of advanced Western models like the MQ-9 Reaper. That power plant allows the Gaza drone to carry 13 precision munitions and operate at a surface ceiling of 35,000 feet. At that altitude, it is entirely immune to man-pads, man-portable air defense systems, like shoulder-fired Stingers, and short-range anti-aircraft artillery. Looking at this map, the evolution is clear. The 131 reaches 900 kilometers. The 136 pushes to 2,500. The Gaza drone casts a 7,000-kilometer radius. To manage these distances, the 149 utilizes satellite communication, severing the line-of-sight restrictions of earlier models. By combining mass-produced commercial components with sophisticated airspace saturation tactics, Iran has successfully bypassed the massive industrial requirements of a traditional manned air force. They have engineered an indigenous strike network capable of reaching across continents, forcing adversary nations to completely recalculate how they defend their skies.